Introduction to vectors. A vector is symbolized a lot of different ways. Some letter, usually V for vector, with this arrow on top. So we say this is vector V. And if we say vector V equals this, two numbers in parentheses with these chevrons, not parentheses and not square brackets. I call these chevrons. When we say the vector -4, 2, we mean if you have a coordinate system, plot the point whose coordinates are -4 and +2. We draw an arrow from the origin to that point. So I'm trying to make this straight. This is vector starting at 0, 0. And the head of the arrow is right at the point -4, 2. So we symbolize the vectors like this, the two numbers with a comma inside chevrons, and the picture is this arrow. This is the vector. When we say the magnitude of a vector, we mean the distance from the origin to that point. Also could be thought of as the length of this arrow. The magnitude of a vector is symbolized like this. Here's the name of the vector, absolute value symbol. Here we could say the absolute value of the vector, or we could say the magnitude of the vector, and it's always equal to the square root of x squared plus y squared. That is the Pythagorean theorem. The distance along the slanted arrow could be thought of as the hypotenuse of a right triangle, where one side is 4. That's this. The distance here is 4. And another side is 2. That would be, that's 2 right there. So here was the vector. Since x squared plus y squared has to equal this side squared, the square root of 20 is equal to r. By r I meant the magnitude of the vector. So x is -4, x squared is 16, y is 2, y squared is 4. And this could also be written 2 radical 5. So what we just did here was, on your sheet of examples, this is example 1. Determine the magnitude of the vector. This is the answer. A vector is something that has magnitude, that means how long it is, and direction. Direction means whatever way it's pointing. All right, example 2. Vector 1 equals the same vector we just looked at. And vector 2 equals 7, 3. And the example is to express vector 1 plus vector 2 in component form. Both of these vectors are in component forms. We call this the x component, and this is the y component. These are in component form. Well, you could probably guess that the answer to this is -4 plus 7 is 3, 2 plus 3 is 5. That's it. One thing that you want to know is what this all means, so we're going to look at a picture. -4, 2, 1, 2, 3, 4, 2. This is vector v1. 7, 3, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3. This is vector v2. The sum of the vectors, the sum of the two vectors, which is this, 3, 5, 1, 2, 3, 1, 2, 3, 4, 5. This vector, besides calling it the sum of the two vectors, it's also referred to as the resultant. And it's actually, this vector that we found, 3, 5, is actually the diagonal of this parallelogram. I just made a line segment parallel to vector 2. And over here I'm going to make a line segment that's parallel to vector 1. So I made a parallelogram. And this vector here, I'll make it red, is the diagonal of the parallelogram, where these two vectors are sides of the parallelogram. All the vectors come from 0, 0. So very easy to answer number 2, and also understand what the answer is. Number 3. Here's another way to represent a vector. A vector could be represented 3, and then in this slanted bracket thing, 37 degrees. When a vector is written like this, the number out here is the magnitude, and this number is the angle that the vector makes with the positive x-axis. The number out here is the magnitude. 37 degrees is the angle that the vector makes with the positive x-axis. So 37 degrees would be in the first quadrant. And then I would measure out from the origin 3 units, a distance of 3 units. So as long as this angle is 37 degrees, and as long as the length of this arrow is 3 units, this would be vector v1. v2 is -4, 290 degrees. So this number out here, I just got finished saying that's the magnitude. Well, that can't be the net magnitude because it's a negative number. So here's what this means. First, I find where 290 degrees is. There's 0 degrees, 90, 180, 270. I'll go 20 more degrees right there. So 270 degrees would be in the 4th quadrant. If this was 4, we would measure from the origin on this vector here 4 units from the origin. The -4 just means take this point that I just found, 4 units from the origin, and reflect it through the origin. So I'll trace in red right there. That's the vector v2. So I found 290 degrees, measured out 4 from the origin on that, The negative told me to reflect through the origin. This red thing is vector v1, and this green one, that's vector, sorry, the red one is v2, and the green vector over here, that's v1. And we're supposed to find vector 1 plus vector 2. And that was really easy to do in example 2 because we just added the x's and we added the y's. Simple. Well, here we don't have the x's or the y's. So we're going to find them using the definitions of sine and cosine. Since the definitions of sine and cosine are cosine of any angle is x over r, cosine x over r, and the sine of an angle, any angle, is y over r. By cross multiplying, x is always r times cosine theta, and y is always r times sine theta. And when the vector is given in this form, with the number out here and a measure of an angle in here, that's r and that's theta. So for vector 1, x is equal to r cosine theta, and y is equal to r sine theta. Those are the x and y coordinates of this point right here, that point. For vector v2, the red one over there, x is equal to r, keep the negative on the floor, cosine theta, and y is equal to r sine theta. These are the x and y coordinates of this point over here in the second quadrant. Just think about this, that 290 degrees is in the fourth quadrant. The cosine of a fourth quadrant angle is negative. I mean, the cosine of a fourth quadrant angle is positive. This is a -4. A negative times a positive is a negative. In the second quadrant, x is negative. The sine of a fourth quadrant angle is negative. So this is saying a negative times a negative. A negative times a negative is a positive. Y is positive. That's why this point is in the second quadrant. X is negative and y is positive. So that verifies this picture is accurate based on this. So to find the vector 1 plus vector 2, which was the direction, the question, I'm just going to say vector 1 plus vector 2, just like in the previous example. We're going to add the x's, which are, I don't remember where they went. Here they are. So we'll keep this here. Add these x's. I mean, this x and this x. So it'll be 3 cosine 37 degrees. Add this x, which is -4 cosine 290 degrees, comma. Now we add the y's. So 3 sine 37 degrees plus the negative, so I'm going to erase the plus sign, three sine 37 plus -4 sine 290 degrees. Chevrons. So if you get out your calculator and put it in degree mode, type all this in, you could say vector 1 plus vector 2 is approximately 1.028, comma, 5.564. Just type all this in. That's where this number came from, 1.028. Type all this in. That's where 5.564 came from. And if you actually plotted this point, 1.028, 5.564, that would be, if you put this red vector over in this picture, the answer that we just got, 1.028, 5 point whatever, is going to be here somewhere. The sum, or the resultant, should be the diagonal of this parallelogram, where the two original vectors are sides of the parallelogram, and the sum of the two vectors is supposed to be the diagonal of the parallelogram. Example 4. Vector 1 equals negative 4 comma 2. Vector 2 equals 7, 3. Find vector 1 minus vector 2. That means negative 4 minus 7, comma, 2 minus 3. In other words, negative 11, comma, negative 1. So here's what this means in a picture. But before I show you the picture, I'll remind you that this subtraction here, subtracting is always the same as adding the opposite. So, if I plot the vector negative 4, 2, 1, 2, 1, I gotta make this bigger. Plot the vector negative 4, 2, 1, 2, 3, 4, 1, 2, from the origin. That's vector 1. And then I'll plot the vector 7, 3, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3. That's vector V2. V2 is the green vector. The opposite of it means reflect this in the origin. So instead of over 7 and up 3, I'm going to go over 7 this way and down 3. So by reflecting this green vector in the origin, that's the vector called negative V2. And so our answer to the question, vector V1 minus vector V2, should be the sum of the parallelogram with these sides, the blue and red. And our answer was negative 11, negative 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 1. This purple vector is our answer. So that should be the diagonal of a parallelogram. So V1 is red, V2 is green, the opposite of V2 is blue, and V1 plus the opposite of V2 is purple. The answer was negative 11, comma. All right, exercise 5, example 5. There's a vector called V, vector V, negative 4, 2. And it says to find 2 times the vector. Well, that just means multiply both of these numbers by 2. And it also says find negative 3 times the vector. That means multiply both of the original vector numbers, components, by negative 3. Negative 3 times negative 4 is 12, and negative 3 times 2 is negative 6. That's it. So you should, I'm not going to do it here, but you should plot all 3 of these vectors on a coordinate system and see how they're related. That's a project for you to do. I'll ask you about that in class. How are these 3 vectors related? Number 6. There's a vector called V, vector V, whose magnitude is 3 and whose direction is 37 degrees. And it asks for 2 times the vector, 2 times V. Well, what you'll discover when you think about what I asked you to think about here is that multiplying a vector by a constant only changes the magnitude. The direction does not change. So there's the answer to number 6. 2 times the vector, that will multiply the magnitude by 2. The direction will not change. So look back at example 5 and you'll see that's verified. Number 7. The initial point of a vector is 3, 1. The initial point of a vector is 3, 1. 1, 2, 3, 1. That's where the vector starts. We usually start at 0, 0, but let's see where this is going. The terminal point is 1, negative 2. So they're talking about this vector. I'll make it green. Initial point, 3, 1. Terminal point, 1, negative 2. The question says to express this vector in this form. A I hat plus B J hat. So what does this mean? Well, first of all, I want to tell you what they want us to do is move this vector so that it starts at the origin. We'd like all vectors to start at the origin, but we want it to have the same exact magnitude and direction. We just want it to start here instead of here. We want it to go in the same direction. In other words, we want it to be parallel to this, and we want it to be exactly the same length as this green one. So since to get from here to here, I could go down 3 and to the left 2. I'll do the same thing from the origin, down 3 and to the left 2. So this is a picture of what they're looking for. We say these are the same vector. I know they're in different places, but we call them the same vector because they have the same magnitude, same length, and same direction. When I say same direction, I really mean they're parallel. So the eye with the hat on it, like that is specifically the vector 1, 0. Oops. Like this. X and Y. X is 1. And in other words, it's this vector. I'll make it blue. And J with the hat on it is the specific vector 0, 1. I'll make that one purple. So there's this vector that starts at 0, 0 and goes to 1, 0. And it's right, so it's right on the x-axis, is the vector that's famously called I. It's the I vector. And this one is the J vector, the purple one. It goes from 0, 0 to the point 0, 1. It's right on the y-axis. Both of these have magnitude 1. When a vector has magnitude 1, it's called a unit vector. So the I vector and the J vector are both unit vectors because they have magnitude 1. And the I means it's on the x-axis, the J means it's on the y-axis. So to write the vector in this form, this will be the third way to write a vector, because we had the component form, and we had the magnitude direction form. Now we have this AI plus BJ form. So look at where this red vector ended up. The original vector they asked about was the green one. It ended up with this ending up here, which is the point -2, -3. So that vector could be written like this. That's one way to write it. But to write it in this form that's in the question, we just take this -2 and put it next to I, hat, and then plus, we take the B, which is -3, and put it next to the J hat. And that's the answer. I'll show you why it is in a second. For number 7, we found the vector -2, -3. Remember that we found that by just moving this vector, the green one, from where it was given to where it would start at the origin. And then, so that's one way to write the vector. And now another way to write it, as I just said, is -2I hat plus -3J. So here's why that's right. I means the vector 1, 0. J means the vector 0, 1. The This is I is always this, 1, 0. J is always this, 0, 1. This vector times -2 means multiply both of these by -2. This vector times -3 means multiply both of these in here by -3. -3 times 0 is 0. -3 times 1 is -3. And there's a plus here. In my mind, I changed -3 to adding a negative. So to add these vectors, add the x's, -2 plus 0. Add the y's, 0 plus -3. So the same vector, -2, -3. Number 8. It says find a vector that has the same direction as this vector. That says find a unit vector that has the same direction as this vector. Find a unit vector that has the same direction as this one. So first thing we do is find the magnitude of this vector. And its magnitude is always the square root of x squared plus y squared. The magnitude of this vector is the square root of 9 plus 4. So this is not a unit vector. The unit vector would have magnitude 1. Unit vector magnitude 1. The magnitude of this vector is not 1. But if we divide both of these components by this number, this vector will be a unit vector, and it will be in the same direction as that. So what I'll ask you about in class is, I'll ask you to prove, you can do this ahead of time, prove that this is a unit vector, because the question said find a unit vector. And also see if you can prove that it is in the same direction as that, the original vector. So here I'm just telling you how to do it. See if you can prove that it's the right answer. Two things about this have to be true. Number 9. Find a unit vector that is normal to this vector. So this vector, -4, 5, left 4, up 5. Since these vectors given in this form, component form, always go from 0, 0 to a point, we could say that the slope of the vector is always going to be y over x. It's actually the change in y over the change in x. But we could just say y over x because one of the points is always 0, 0. So this is the point -4, 5. The change in y is going to be 5 minus 0, in other words, just y, over the change in x will be -4 minus 0. In other words, it's just the x. So the slope of this vector is -5 plus. A vector that's normal. Normal means perpendicular. Normal means perpendicular. The slope of a normal vector is going to be the negative reciprocal. So we want a vector that has this slope. All our vectors start at 0, 0, but the slope is y over x. So there's x, and there's y, 5, 4. All right, so we're almost done with this problem because this vector is normal. because the slope of this and the slope of this are negative reciprocals. Remember, that's y over x. Slope is changing y over changing x. So why isn't this the answer? Isn't this a unit vector that's normal to that? The answer is no. It is normal. Oops. This vector is normal to that, but it's not a WAC. It's not a unit vector. A unit vector has to have magnitude 1. The magnitude of this vector, because the magnitude of that vector is the square root of x squared plus y squared. So the magnitude of that vector right there is the square root of 41. That means if we divide both of these components by that, we will have what we're looking for. 5 divided by radical 41, comma, 4 divided by radical 41. So your job is to prove two things. One is that this really is a unit vector, because it said find a unit vector. Also, can you prove that this vector is normal to the original vector that was given? By normal, we mean perpendicular. And we will save example 10 to do in class.